If you're a physics student, then you need to know how to solve this differential equation, whether a is greater than 0, less than 0, or equal to 0. Okay, first up, a is equal to 0. Well, that's the simplest case. You just integrate with respect to time twice, and you get this as your solution. And this, of course, makes sense because the differential equation is telling you that x is the function such that if you differentiate it with respect to time twice, then you get 0. So at most, x can be an affine function of t. So what if a is less than 0? Well, then I can define a to be equal to minus lambda squared, where lambda is some real number. And then this differential equation is saying that x is the function such that if I differentiate it with respect to time twice, I get back that same function multiplied by minus lambda squared, where lambda is some constant real parameter. So if you think about it for long enough, you'll realize that sine and cosine share exactly this property. So if I take sine of lambda t and I differentiate this twice with respect to time, you'll see that I get back minus lambda squared times sine of t, so minus lambda squared times the original function, and similarly for cosine. So our general solution is just a linear combination of sine and cosine with arbitrary constant coefficients. Now you might be thinking, I know two other functions that satisfy exactly this property, namely e to the I lambda t and e to the minus I lambda t, and you'd be correct, but we know that these are related to sine and cosine through Euler's formula. So the final case is when a is greater than 0. So again, we can rewrite a, but this time as lambda squared, and then this differential equation is telling us that x is the function of t such that if I differentiate it twice with respect to t, I get back lambda squared multiplied by that function of t. So if you think before we had minus lambda squared, but now we have plus lambda squared. So what functions satisfy this condition? So maybe the more obvious functions that satisfy this condition are e to the lambda x and e to the minus lambda x. So again, our general solution will be a linear combination of these. However, there's another pair of functions which also satisfy this condition, namely hyperbolic sine and cosine. But again, we know how these are related to e to the lambda x and e to the minus lambda x. So again, it's equivalent as a solution. So whether or not you express the solution to the negative case in terms of trig functions or complex exponentials, or the positive case in terms of hyperbolic trig functions or normal exponentials, really depends on personal preference, but also sometimes paying close attention to the boundary conditions can make life a little bit easier when trying to fix the various arbitrary constants that appear in your general solution.